Now I want to talk about the most dangerous misconceptions in healthcare AI, and that is the illusion of high accuracy percentages automatically mean good performance, meaning that the product is saying that, hey, I have the highest accuracy. That does not necessarily mean that you are actually treating the patients properly and your performance is good. Let's say someone shows you an AI model that has 80% accuracy in predicting patient outcomes. That's pretty good, right? But here's the problem. If 80% of your patients are stable and only 20% are at risk of complications, a model would achieve 80% accuracy by simply predicting that every patient will be stable. Now, look at this again. This is very important. If the AI model was trained on, let's say, healthy patients, stable patients, and your clinical practice in your hospital, let's say 50% are actually serious and sick patients, then this AI model will not be good for you. And although on its own data set, this AI model performs well, however, this AI model will not perform well in your hospital, in your clinical setting. That is very important to understand. And as the human in the loop, these are the very questions that you will be looking at, and you will be looking at the data from the vendor, and you will be looking at your own data. Hey, does that product actually represent my clinical scenarios? And this model would be completely useless for identifying patients who actually needed interventions, but it would still show impressive accuracy statistics. But your outcomes at the end of the day will not be good. In healthcare, this kind of false confidence can be deadly. False negatives, meaning missing patients who actually are at risk or have the problem. And this can literally cost lives. And a 1% miss rate in cancer screening might sound small, but this represents thousands of missed diagnoses across a large population. Now, that is a different conversation that you see that, okay, what is the miss rate of cancer screening by a human, perhaps, right? The human miss rate might be, let's say, 2% or 3%. And somebody will argue that if an AI is bringing in a 1% miss rate, that is better than a 2% miss rate or a 3% miss rate. But of course, this has to be seen with every specific situation. And that again is where you, the human in the loop, will come into the picture to evaluate these models. And that is precisely why we need to look beyond simple accuracy metrics. We need to understand sensitivity and specificity, positive and negative predictive values, and most importantly, we need to understand how the model performs on the cases that matter the most. And we're going to talk all about that in this program. So think of it this way. If you are developing an AI system to identify patients at risk for sepsis, you care much more about catching every case of sepsis than you do about overall accuracy. You want to catch all those cases, right? You rather have some false alarms than miss a single case of sepsis. Now, that will be a valuable AI if it does not miss a case of sepsis. It may give a few false alarms. However, you don't want all the false alarms. You don't want all the false alarms. And that is, again, where you come in to see if this model is good for you. Too many false alarms could not be good for the clinical setting as well. As we all know, false alarms are a pain for any clinician. And as we say that AI is not replacing humans, and this is where your clinical judgment becomes essential. You understand the clinical consequences of different types of errors. You know what conditions require high sensitivity versus high specificity, and we'll define these things soon enough. You understand the trade-offs between false positives and false negatives in different clinical contexts. A false positive for one may not be as important compared to a false positive in another clinical scenario. So when vendors show up or vendors show you an AI tool with impressive accuracy, you need to ask the right questions. What was the prevalence of the condition in your training data? How does the model perform on the specific types of patients that you see here, actually? And what happens when the model is wrong? Does it pick up? Does it have any reinforcement learning installed? To recap this, the dangerous illusion of accuracy. High accuracy percentage can be dangerously misleading in healthcare. Example, say your model is 80% accurate, but 80% of your data is non-critical patients, and your patients are different. It might be learning to always predict stable patients and ignore the ones who truly need help. Now, this is the accuracy paradox. So, look over here. If you do, overall accuracy is pretty good. It's pretty good, right about this mark over here. However, accuracy for critical cases is not that great, is definitely not that great. Now, in medicine, false negatives mean people die. And 1% miss rate in cancer screening is thousands of missed diagnoses. You must evaluate data balance, not just accuracy. Dear all, I hope you are doing great and that you are liking these lessons and you are enjoying and you are learning. And I did want to suggest something as an option for you. Only if you are one of those who want to have this content in a more organized manner, there is a program that I have set up that you can find in the description. It absolutely is not necessary. However, it is only for those who do thrive in an organized approach, and there just might be a few more goodies there as well. Anyways, I wanted to share this, and now back to the video. Now, this diagram perfectly illustrates one of the most dangerous problems in healthcare AI. That is algorithmic bias due to unrepresentative training data. Now, let's have a look at this. Now, look at the left side. So, algorithm training. Notice that the training data contains a very limited range of patients' types. You can see that all of these figures, we get a different color. You can see that all of these different images, they are similar looking. They all look the same. These all images look the same. This could represent training data that is predominantly from one age group, one ethnicity, or one socioeconomic background. Now, the algorithm, your model, learns patterns from this limited data set and creates what it thinks is a trained algorithm, represented with this neural network pattern here in the middle. This is your trained algorithm from this data and model. See what happens during algorithm application on this right side. Now, when this algorithm encounters the real world, a more diverse patient population is there with different ages, ethnicities, and backgrounds. It struggles. Now, you can see all the different types of patients, young, old, black, white, all types of patients. Now, you are using this model for this population, and let's say you're looking to detect early Alzheimer's disease, you will have a problem. This algorithm will correctly identify some patients who match the training data. They may be labeled as early Alzheimer's disease, but look at the bottom. Patients who don't match the training data profile get misclassified as no early Alzheimer's, even when they might actually have the condition. This isn't a hypothetical problem. We've seen this happen with pulse oximeters that are less accurate on darker skins, diagnostic algorithms that are trained primarily on male patients missing conditions, similar conditions in females, and AI tools developed in academic medical centers end up failing in community hospitals because this whole scenario is different. The key message here in this example is that the training data contains a very limited range of different types of patients. And when you apply this algorithm to a broader patient population, this will cause the algorithm to classify many patients with an unfamiliar profile erroneously. This is why diverse representative training data isn't just a nice thing to have. It is important for patient safety. And this is why your clinical expertise in identifying these potential biases is absolutely essential, as you will be the human in the loop.